Good morning. Now, in today's class about nuclear reactions, we will learn about isospin. Okay, you know what a nucleon is. That is, protons and neutrons are together called by the name nucleon. Now, interaction of nucleons actually does not depend upon their spin orientation, that is whether it is having a spin up or spin down. If it is having a spin up, we will have ms is equal to plus half, and if it is spin down, we will have ms is equal to minus half. So uh, generally when we are considering the interaction between nucleons, the direction of spin orientation does not have any significance. However, multiplicity of spin orientation will have importance. That is, for nucleon, multiplicity is 2. Whether it is proton or neutron, its multiplicity will be 2. So, when considering nucleon interactions, the direction of spin orientation does not have any importance, whereas multiplicity of spin orientation has a significance, but that also will become unimportant in those situations when a magnetic field is applied. That is, when a magnetic field is applied, then the nucleon interaction will depend only on its spin component relative to the direction of the applied magnetic field. We know that nuclear forces are charge independent. As already said, the formalism of nuclear interactions may depend on the multiplicity of nucleon state, which is 2, but it is independent on whether the nucleon is proton or neutron. So it doesn't matter whether the nucleon under consideration is proton or neutron, that doesn't matter, but the interactions or the nucleon interactions depends on the multiplicity of spin orientation. Now, the only exception is in the case of electromagnetic interaction. Here, there is distinction between proton and neutron. Okay, that is, in nuclear interaction or in nuclear reactions, we are not bothered about the nucleon under consideration. Okay, that is, there is no distinction between a neutron and proton, but this is not the case with electromagnetic interaction. There is a clear distinction or between protons and neutrons. Okay. Now, this two-state degeneracy, it actually lead to the formalism of magnetic interaction of spin half particle. That is, we know protons and neutrons are treated as two different states of a single particle and is called by the name nucleon. And this nucleon is assigned a spin vector. That spin vector assigned to the nucleon is called by the name isospin. Now, the two degenerate nuclear states of the nucleon in the absence of electromagnetic field are called isospin up. It is mainly assigned to proton, and the other one is isospin down, and it is normally assigned to neutron. Okay, so for a nucleon with the isospin quantum number T is equal to half, proton will have mt is equal to plus half, whereas neutron will have mt equal to minus half. Now, all these projections are measured with respect to an arbitrary axis. That arbitrary axis is called by the name 3 axis, and it is labeled as 1, 2 and 3 just to distinguish from the general XYZ coordinate system. Now, as usual, isospin obeys the angular momentum vector rules. That is, suppose that you are considering an isospin vector t, then it will have length root of t into t plus 1 h cut, and its 3 axis projections will be t3 is equal to mt h cut. So when asked about isospin, these three slides are very important. This one, especially this third slide. Okay. Next, we are going to see about the various coupling rules associated with the isospin. A two nucleon system, we are considering it as an example. Suppose that it has a total spin, isospin T. Total isospin is represented by the letter capital T. It will have the total isospin T as either 0 or 1. Okay. Now, then T3 is called total isospin vector. So, the 3 axis component of the total isospin vector T3. So, T is total isospin, whereas T3 is total isospin vector. That T3 is nothing but sum of the 3 axis component of individual nucleon, and it is given by T3 is equal to half Z minus N. Z is a proton number, N is a neutron number. Okay. Now for a given nucleus, this total isospin vector T3 is determined by the number of neutrons and protons. For any value of T3, total isospin content number T can have any value greater than modulus of T3. These are the various values that the total isospin T and total isospin vector T3 can have. Now another fact about isospin is that if the nuclear interaction that we are considering is charge independent, then the three axis projections of T equal to 1, which are the three projections plus 1, 0 and minus 1. Okay, so the three axis the three axis projections of T equal to 1 will have same energy, whereas the single T equal to 0 state will have different energy. Okay, so this is the statement. So in order to clarify the statement, they have given an example above. So there is, if you want, you can quote this example also, otherwise you can just write the statement. Okay, now then about isospin assignment, they have given an example for carbon 14 and nitrogen 14 and oxygen 14. For nitrogen 14, T can give a 3-axis component of 0. Okay, and the possible values of T can therefore range from 0 to a maximum of value of 7. That is in the case of nitrogen. Okay, now the tendency towards nuclear symmetry means that lowest state will have T equal to modulus of T3. That is, lowest state will have the smallest possible value of T. Okay, this is also applicable to ground state also, but in the case of excited state, they are mainly assigned, their values for excited states are mainly assigned on the basis of reaction studies or decay studies or symmetry arguments. Now there is another state. We know that the energy that each state can have is mainly due to the presence of nuclear force. Now the energy of 0 plus state, that is another state, 0 plus state, in the energies of 0 plus states in the case of all nuclei will be the same or will be identical, and these states are actually T equal to 1 triplet state. Now some of the selection rules associated with angular momentum coupling theory. One is that delta T, that is the change in total spin, the change in total isospin, that is delta T, it must be 0 or plus or minus 1, except for the transitions from T equal to 0 to T equal to 0 are forbidden, and delta T equal to 0 transitions are forbidden in the nuclei with the T3 equal to 0. So that underlined portion is actually the selection rule. Now again an example for nitrogen 14 transition, delta T equal to 0, then that transition is forbidden as per the selection rule in the case of nitrogen 14. Now consider a decay, another decay, that is the even decay. It is called even decay. That is the decay from energy state 1 to the energy state plus 1. In such case, T equal to 0. That is, ground state is prohibited by the selection rule. Ground state is not allowed in even decay transitions, whereas even decay to 0 plus state with the T equal to minus T with the T is equal to 1 is permitted. So even decay to plus 1 state with the T equal to 0, that is ground state, is prohibited, whereas even decay to 0 plus state with the T equal to 1 is permitted. That is another rule. Then the higher energy transition results in greater intensity, whereas lower energy transition intensity will be only twice the original intensity. That is, the transition higher energy transition will have higher intensity, that is of the order of 5. Okay, whereas low energy transitions increase in intensity will be only twice. Okay, the other one is 5 times, whereas this one is only 2 times. Now similar is a selection rule for beta decay also. uh, there is a decay called mirror decay, and that is, in such decays the transition is forbidden unless delta T equal to 0. Such decays are mirror decays, whereas in non-mirror decays are those with delta T is equal to 1, and the Fermi contribution to transition is reduced by several orders of magnitude by the violation of isospin selection rule. So that distinguish between mirror decay and non-mirror decay. That is a probable question. Then nuclear reactions also show effects of isospin. That is, the 3-axis component is automatically conserved when number of protons and neutrons remain constant. But it is also true that total isospin content number T remains invariant in transition. So just consider a reaction, that is, oxygen and hydrogen are the reactants and the products are nitrogen and helium. Okay, so the reactants have T equal to 0, that is, they are in the ground state. In such case, the total isospin content number T will be conserved only if the products, that is nitrogen and helium, are also in the ground state, that is T equal to 0. So in this case, the excitation of helium is not possible in low energy reactions. Okay, so it is expected that only T equal to 0 excited states can be reached in the case of nitrogen 14. The T equal to 1 state should not be populated. So since excitation of helium is not possible in low energy reactions, a T equal to 0 excited state can be reached only up to that state, that is only up to T equal to 0 excited state can be reached in the case of nitrogen 14. And another thing is that T equal to 1 state, it should not be populated. Now if it is populated, then it will be due to some isospin impurities present in the reacting particles. Now the cross section of T equal to 1 state is observed to be about 2 orders of magnitude smaller than the cross section to T equal to 0 state. That is, cross section to T equal to 1 state is 2 orders of magnitude smaller than the cross section of T equal to 0 state. So that is that statement. That statement shows us the effect or the impact of isospin selection rule on nuclear reactions. Now the members of isospin multiplet, as for example, pairs of mirror nuclei or a set of 3 states are called isobaric analog states. They have identical nucleon wave function. Carbon 14 and oxygen 14 ground state. The nucleons are strongly coupled pairwise. Now analog states are obtained by exchanging a proton for a neutron, and they are strongly populated in beta decay and also in proton neutron or neutron proton reactions. Then in medium and heavy nuclei, placing a proton into a state formerly occupied by neutron involves large energy transfer. Why? Because a neutron number is greater than proton number. Then the newly placed neutron thus will occupy a higher shell model state than the former proton. Now analog states appear in medium and heavy nuclei at energies of 10 MeV and above, and thus they generally do not contribute to low energy reaction and decay studies. So this slide tells us about the definition and the peculiarities of isobaric analog states. Okay. For today, this is enough. Thank you.